hypothesis size of the, or since k is also less than k is the basically number of hypotheses within the hypothesis space. So k has to be less than the total size of the hypothesis space. So finally, this probability that at least one of them would be consistent, which means your version space is not epsilon exhausted, is that it should be less than this value, right? So the maximum probability of providing a consistent hypothesis with error greater than epsilon should be delta, and hence for a PhD learner, this value should be less than equal to delta. This value should be less than equal to delta. So that is the implications. That is the implication.
Sir?
Yeah, there is a question.
Sir, how is that k into 1 minus epsilon naught whole to the power m is coming?
Yeah, what is your question?
Sir, how is that k into 1 minus epsilon naught to the power m is coming?
Yeah, I mean that is what it is explained here. See, what is the probability that one sample, say if I say the all m samples, consider just one sample. What is the probability of error of probability that sample is correctly labeled by h?
1 minus epsilon.
1 minus epsilon, which means all m samples are correctly labeled with probabilities 1 minus epsilon into m. This is the minimum. This is the minimum probability. So this is the maximum. So see, the error is, this is with error, that is the minimum. Epsilon is the bound. So this is the maximum probability of all samples could be correctly labeled by h. This is the maximum probability, right? Which means this h is consistent with respect to training sample. What is the maximum probability that it would be consistent? This is 1 minus epsilon to the power m. Is it clear? Now you consider in your hypothesis there are k such hypotheses, because it is only one hypothesis, but there could be multiple hypotheses which are consistent to your training data, but whose true error is greater than epsilon. We want that none of them should be in your version space. Okay, we want none of them should be in your version space. That is that. So probability that at least one of them, at least one of them would be consistent is this. Sorry, none of them. It is one of them. At least one of them should not be in your version space. So probability that at least one of them would be consistent is because any one of them, if it is if it is chosen, then this is the probability.
Sir, but are we not counting something extra, like we are suppose assuming that one hypothesis is consistent, so it is 1 minus epsilon naught to the power m. Then again we are considering the second hypothesis is consistent. So
Right.
there can be
So
some
for
intersection,
every consistent, right? Yeah, for every consistent hypothesis, 1 minus epsilon to the power m is the maximum probability that it would be. I mean, 1 minus epsilon to the power m is the maximum probability that its true error is greater than epsilon.
Yes, sir.
Right.
Yes.
Now, so since in your version space you do not want, and suppose there exists k such hypothesis. So if you consider there are k such hypothesis in your version space, right? With your so they are all consistent, right? Then the probability that their maximum, I mean, they could be, any one of them could be included. I mean, there the probability would be k into 1 minus epsilon to the power n. Any one of them can be included in your version space.
Sir, it is a maximum bound, right? Because otherwise,
It's a maximum bound. That's why it is written like this, no?
Oh, okay, sir.
So now k is a subset. Basically, k hypothesis is a subset of the total hypothesis space. So that's why this value, using this value, you can say that this value is less than this. So k into 1 minus epsilon to the power n is less than actually this. Okay. I think it should be is not epsilon exhaustive. Either epsilon exhaustive definition is, it should be greater than epsilon. I will check with the book. It may be that it is not this. I will check with that. Yeah, actually, that is what it is trying to say. That this is the maximum probability. So you can consider that maximum probability of providing a consistent hypothesis with error greater than epsilon is delta. So if you want this delta, this a mod h e to the minus epsilon m should be less than equal to delta. And from there, no, you can get also bound of the number of training samples. So if you apply this logarithmic operation and you do the equation adjustment, because the negative will be, if you remove the negative sign, then the less than will become the greater than sign. Okay, so I hope you understand that part. So then you will find that actually m should be greater than equals this. So this is a kind of indications that how the training sample should be there for a PSC learner. So this is a relationship with respect to delta, epsilon, and h. So your epsilon is very small, you require more number of training samples. If your delta is very small, you require more number of training samples, but the rate of increase is different, right? There it is logarithmic. Similarly, the increase of the number of training samples, that is also proportional to the size of the hypothesis space, but that is also in the logarithmic scale. Already, as you say, understand that in our bound, we have taken the maximum number, that size, so it's an overestimate in other way, but it gives an indication. So m grows linearly with 1 by epsilon and logarithmically with 1 by delta, and it also grows logarithmically with mod h. So some of the examples, if we take, it would be much more clearer. Suppose we have these target functions of n Boolean attributes in conjunctive forms. The kind of case we have studied, it is in that form itself. So in this case, each literal can have 3 values, as you know, that it can have true, false, and ignore. So suppose this is the Boolean attributes. So you can have true, false, and ignore in this form. So it is a special case of that. So a hypothesis in the same conjunctive form of a literal, then in the hypothesis space 3 to the power n, it is basically a special case where only we are considering these 3 cases, either true, false, or ignore. So the hypothesis space is size is 3 to the power n, and if I consider the size of the number of the training samples or size of the training set, then this should be for given epsilon and delta and n, it should be greater than equal to this with these relationships. And suppose there are 10 Boolean attributes, then the errors are given such that epsilon is bounded by 0.1 and epsilon is 0.1, delta is 5%. Then you get m as 140, which is quite, number is quite small with respect to the kind of data I usually handle with machine learning. So it's a very simple case for which we can see that with this number and with that kind of characterizations, expectations, you can get some learner. So this is one kind of understanding that when you are learning a concept, how training samples affect the quality of learning, and apart from that, it depends upon also the for the quality of learning. You also try to see that in the probabilistic term, you are trying to arrive at a higher probability to some hypothesis which will be closely or which are very approximate to the correct target concept. So it is not the true target concept, but it is very close in the form of performance, because you are keeping the probability of error, which means error of differences. That is, error means the differences. There are differences between the functional values of target concept and also hypothesis. Now, there is another thing we would like to see also, that what is the power of the hypothesis representation, rather I should say, that form of the hypothesis, which also determines the size of the hypothesis space. Now, how do you consider the corresponding capacity of representation? So, and in fact, in that case, hypothesis space could be infinite also. Right? Suppose I consider in your hypothesis representation, say your variables, input variables, and your levels, or I should say output variable also, output predictions also. Now they are related by a linear model or affine relationships, which means you have these equations like linear equations plus the constant term. So you can have it's a regression formulation of the model building. But in that case, the coefficients of that equation for the model, those are all real numbers. If you consider they are real numbers, so naturally your hypothesis space will be a real space of higher dimension. Depends upon how many variables you are considering as an input variable. So what is the dimensionality of your input space? So depending upon that, you can have an hyperplane representation of the relationships of this model. But then your input space itself, or for the model space or hypothesis space itself, is infinite. So let us try to understand in that context. So let us try to understand first what is meant by dichotomy when I give you a set of instances. So a dichotomy, by definition, it is when you have actually two levels situation. That means there could be two classes, or there could be two levels only. Either an instance is positively labeled or negatively labeled, or we call it positive example or negative example. So consider you have a fixed set, a finite set, finite number of instances. Now keep instances fixed, and you label them arbitrarily. That means you label them either positive or negative. So which means you are partitioning them into two groups or two sets, one with all positive examples, another with all negative examples. Now this is a dichotomy. Now all possible dichotomies means all possible such partitionings, right? So as you know that number of all possible dichotomies in this case would be 2 to the power of cardinality of that set. Is it clear? That should be number of all possible dichotomies. So this is a definition of dichotomy. I understand it should be trivial for you to understanding this thing. Only thing is that you should note what is meant by dichotomy, the term dichotomy here. It is the labeled samples with some kind of partitioning, a kind of labeling, or an instance of labeling over the samples, something like a function. So if I say it's a dichotomy is defining one particular function, right? And there are 2 to the power cardinality of S functions. Now, shattering by a hypothesis space H, that is also another concept that you need to understand. What is meant by shattering? Now, shattering means shattering of a hypothesis, shattering by a hypothesis. That means if there is a hypothesis which can uh, make the correct predictions on these dichotomies. So which can satisfy the dichotomy or levels of dichotomies, right, of a particular dichotomy. So that hypothesis shatters that dichotomy. So let me give you an example. Suppose I have 3 points, okay? Let me have 3 points. Say 1, 2, 3, these points. And I have labeled them arbitrarily. Say this is plus, say this is plus, and say this is. So shattering would be, suppose my hypothesis representation is a straight line. So a straight line defines a particular hypothesis in such a way that one half plane of the straight line would contain the level positive and another half plane will contain the level negative. So that is what shattering means. Because if I get the straight line equation, then I can use algebraic equation to, algebraic computations, but put that value and you know that in the positive half plane, the value would be positive and the negative half plane, the value will be negative, depending upon how you are arranging the straight line equations, right? But anyway, you can do that. You can make an equation in that form and you can shatter it. So this is a shattering. But when I say shattering by a hypothesis space, this is shattering by a particular hypothesis. But when I say shattering by a hypothesis space, it means that with all possible dichotomies, there exists a hypothesis which shatters it. So, for example, this is one labeling. Let us consider this is negative, right? Instead of this, let us make it negative. So now these two are negative. This is positive. So I can draw another straight line. So this straight line shatters this labeling. I'm not changing the instances. Instances are fixed. I'm just changing the labels. I'm getting another dichotomy. So like that, all possible dichotomies. So there would be 8 such cases because there are 3 instances. So there will be 8 such cases, and for each case, you should find a hypothesis which will shatter it. That is a straight line which will be shattered. Now, if it happens, then we say this instance, this set is shattered by the hypothesis space itself. So that is what shattering by a hypothesis space is. Shattering of S by a hypothesis space H. Is it clear? Is there any doubt? So this is the definition. Let me just rub this. So that is what, if there exists a consistent hypothesis for every dichotomy of S. What I described, that is formally stated in this section. I hope it is clear to you. Now we come to a very interesting and important concept which you will find in machine learning literature many times, that there is a concept called Vapnik-Chervunin-Kiss dimension, or in short, VC dimension. Now this VC dimension is telling that what is the capacity of a representation of your hypothesis in terms of the power of shattering of certain sizes of instances. So it says that what is the maximum number of maximum size of the instances of S, in this case S, maximum size of a set of instances which can be shattered by the hypothesis space H. So the size of the largest finite subset in X shattered by H. So if I take a larger than that, set X, if we have more number of elements in X, then you will find that it is not possible. So there would be a dichotomy which is not be, no, you will not find any hypothesis which will be consistent with respect to that. So we say it is consistent, right? So you will not find any consistent hypothesis, which means your Gaussian space will be empty. So we are telling you now that the power of the representations, and in the previous class itself we discussed about inductive bias, that why we require inductive bias, which will constrain the size of your hypothesis space. And because of that representation, your versions, though there may be true, there are true concept target functions, but target functions are not representable for that kind of data points or that kind of levels. So this is what. So it says that this is a Vapnik-Chervonenkis dimension. It is a number. You can say actually it is the cardinality of a set. Cardinality of a set. Right? So the maximal finite subset which could be shattered by H. Now there are some more understanding is required. I will discuss once we go through these slides. But one fact, very trivially, you can notice that this dimension is less than logarithmic of the size of the hypothesis space. So this proof is direct that if H requires 2 to the power d distinct hypotheses to shatter d instances. I mentioned in the previous case, you require 8 straight lines to shatter 8 instances of the levels of 3 points. So you require 2 to the power d distinct hypotheses for d instances, which means that your 2 to the power d should be less than, again like that. The distinct hypothesis is a subset of H itself, so it should be less than the whole hypothesis size of the whole hypothesis space, and from where you get this particular relationship. And D is here so your D is basically less than, it is the maximum. This is a maximum number. In fact, that is what Vapnik-Chervonenkis dimension or VC dimensions property, that if there exists any such finite subset, that is sufficient. So it need not be shattered. It need not shatter all subsets in X. If there exists any such subset which is shattered by H, then we consider that is a candidate for your VC dimension should be at least greater or equal to that number, because there may exist another a size greater than that also. But at least if you find any set which is shattered by H, that cardinality itself can tell you that its VC number is at least that cardinal, number. The proof that it is more than that, it is not possible. That is a bit complicated. But from the empirical point of view, if you can find some examples which can be shattered, which means it is fine, it is done. So with respect to the examples what I have given, you can find that those 3 points, if they are non-collinear, they can be shattered by 8 such hypotheses. But if they are collinear, then you will find some combinations are not going to be shattered. But that won't be considered, because there exists 3 points which are shattered by straight lines representations of hypothesis. So with that representation, we can say that VC dimension is at least 3. In fact, it can be proved that that is 3. If you take 4 points, then it cannot be shattered by straight lines. I mean, no instances of 4 points can be shattered by a hypothesis, by a straight line. So those proofs are again complicated. Now, some of the examples of this VC dimension, say you consider set of intervals in real axis, which is the hypothesis space. Any interval you consider. So the idea is that if a point is included in that interval, then your output is 1. Otherwise, your output is 0. Outside that interval, output is 0. That is the hypothesis. So that is the level. So I will give you a particular value, which is a value, a real number, and then the labels, plus either positive or negative. So you have to find out an interval which will satisfy all positive examples and also satisfy all negative examples. That is then that hypothesis is consistent. Now, this is the case. Now, you can show that if you take 2 points, there is no issue. If you take 2 points, always know that interval forming those 2 points will be fine to consistent, right? Either if both are positive, you can take both of them in one interval. If one is positive, you can take some interval including that positive. If one is other way also. So you know that it is trivially you can show that given 2 points, your this hypothesis, interval hypothesis representation, it shatters. So BC dimension is at least 2, and you can also show that no, if I have 3 points, then it is not going to be shattered. So if say this is the case, you can show that no H is shattering. No, say 3 points, P less than Q. Anyway, there would be always, because there are 3 points and distinct points you have to consider. So this order will be always there in the real axis. Huh? And then you find that there is a configuration for which you cannot find any interval. Like you say P and R is positive and Q is negative. So you will not find. So Q is the middle point. The 2 endpoints are positive and middle point is negative. Or the other way, 2 endpoints are negative, middle point is positive. You will not find a single interval which will shatter them, right? No, middle is negative, then you will not find. If middle is positive, you will find. So PR is positive and Q is negative. Then you will not find the interval. So which shows that the BC dimension is 2 in this case for this kind of hypothesis. You continue with that straight line example. I am not repeating that. I have already mentioned that it's actually with 4 distinct points, it cannot be shattered. And so there exists a dichotomy each containing a pair of points non-separable by a straight line. So this is an example which has been shown here. Suppose you have the labels with 4 distinct points. The 2 diagonals are having, say, same levels. If you form a quadrilateral, say 2 diagonals are having same levels, then there does not exist any straight line which will shatter. So that is the proof. So which means that only the BC dimension is 3. Okay, so its BC dimension is 3, and you can extend this proof to show that in a d-dimensional space with d minus 1 dimensional hyperplanes, BC dimension is d plus 1. I hope the generalization is understood. So d-dimensional with respect to this plane, what is the dimension of the space? 2. What is the dimension of the hypothesis? So dimensional hyperplanes. What is the dimension of the? So it is straight line. So dimension is 1. That is why d minus 1. And what is the BC dimension? It is d plus 1, which is 3. You can generalize this result. So another example. So this example is that you have all axis aligned rectangles in a 2-dimensional space. So like intervals, if you extend the concept of interval in 2-dimensional space, it becomes a bounded rectangle. Instead of an interval, it's a bounded rectangle. So any point within that rectangle will be labeled as a positive, and outside that rectangle will be negative. So if that is the kind of classification, that is the kind of, so representation of hypothesis will be they do this close to corner points. Now you can show that it is not possible to place 5 points anywhere for shattering. So 4 points, there is a 4 point, it can shatter maximum 4 points. That can be shown. So this is one example. One example that with all possible levels, it is taken from this book, FM Alperin's book, you can check. But it can be proved that no, there are 5 points which cannot be shattered. So which means its BC dimension is 4, right? So this is what you should once again note, that if there exists any such subset which can be shattered, now that is sufficient to say that its VC dimension is at least that number, that cardinality of that set. Well, the significance, it's a bit, I mean, it's a measure, interesting measure, but no, it is trying to tell you some sort of model capacity and complexity, not very in a precise way, but it's an indicative figure. So higher dimension of higher capacity and it is more complex. But there is an issue here, catch here. Suppose LUT, which is lookup tables, LUT is lookup table here, and we have already discussed that it is basically inductive bias in the lookup table is 0. So it's a very powerful representation, but it's not useful in that sense that for small data it is okay. For a large data set, this kind of representation is impractical to maintain that, to search, to space. From that point of view, it is not very practical. But in some cases, you use it. Now, there, VC dimension has infinite capacities because you can shatter any LUT is a representation schemes. So if you increase the dimensions, so it will go on. It can take as many as samples. It can take as many as samples from your input space. So that's why it's a bit pessimistic neighbor. Now let us come to the other kind of consideration. So I discussed about the case when the training sample is not having any error. But now you consider even your training sample is also having error. Now, how do you handle that? So that is the noise part we are talking about. So in your data itself, training data itself, there is a noise. So there are three major sources of getting that level data noisy. Your imprecision in your measurement of features, error in leveling, we call it teacher noise, and you may miss additional attributes in representation. So your representation itself is not reflecting the total variations of the data, variability of the data and other things. It is not capturing that. So there could be some other attributes, latent or hidden, which is not captured in your representation. So that's why even when you, that's why the levels what you get, that may not be, you cannot consider training error is 0 or the training data set is error free. You may have noise. And that's why you may not get a consistent hypothesis. And even if you get consistent hypothesis because there is an error, it has also an issue with respect to true error. So that is why many of the machine learning techniques, in fact, all the machine learning techniques subsequently will be discussing, we'll see that you have to tolerate a training error within a limit. And also we'd like to see that your model remains simpler. See, this is a trade-off. This is a trade-off. Now, you may get a consistent hypothesis even with your representation, but since there is an error in training error, though your training error, since there is also error in training samples, so though you can make your training error 0 by choosing a consistent hypothesis, but your generalization will fail. So you'll get high test error or true error. So, so the inductive bias is important. We have seen. I think let us. That is what I was telling you. That if you have low training error, still you will get high generalization error. So, to what extent a model trained on the training set predicts the correct output of new instances? That is called generalization. Naturally, if you have more training samples, you are going to get a better model fitting and your generalization error will be lower. But there is another issue that even your choice of your representation of hypothesis, that should be matching with the corresponding target functions, the representation of the target function. So if your target function itself, that means the process which is describing the relationships between your instance and also your level, if that process has certain complexity. Now, if your model is more complex than this, you may get a good fit for the training error, but that is not really representing true model, so you will get higher generalization error. So these are certain things. So the complexities are also should be appropriately chosen. So that is another trade-off. So you have lower complex model, it will have higher training error and also generalization error, but if it is appropriate one, you will get both the error low. So that is the kind of choosing choosing the appropriate complexity of the appropriate model is something like this, that you try to keep both training and the test error, which the term I will come, or validation error, both of them you try to keep them low. So that is the indication that actually your selection of model is more appropriate. Anyway, the situation when it happens, we call it underfitting. So we have chosen a model which is lower, whose complexity is lower. So you need a more powerful model. You need to, suppose you are using only the linear form in your model for predicting any output given input variable. So that is less powerful than if you use a polynomial of degree 2, right? But and if that is the process, in the process itself we require that kind of relationships. So you will find both training error, you are not going to fit that model very well. So you will get higher training errors. That is the indication. So if you are not able to get training error within certain, within the desirable limit, you have to think about changing the model or increasing the complexity of the model. On the other hand, as I mentioned, that if you have higher complex model, you can fit training sample easily. Say you have 8 points. So if you have a polynomial of degree, say 7, that means which will have 8 coefficients exactly, you can fit it, you can get 8 equations, maybe you can solve them, you can get a model. But those 8 points, say they are actually related by some straight line itself, say in a 2-dimensional, say dimension is 2. But then it is deviating much from the true representation of the model. So though your training error is low there, or 0, it may be 0 also, it may be low, but no, you have a very high generalization error because it is not reflecting the true relationships for unseen cases. And in that case, we call that situation as overfitting. Your model is overfit because you are getting very low training error. When you apply that model with the test data set on which the model is not built, that is meant for testing only, or validation data set, which some will say, we'll see a subtle difference between these two. So there, if you there you will get higher error. So if you are coming to that situation, so we call it overfitting. So it is kind of by looking at the combination of these two errors, you are trying to understand that how good is your model, how appropriate is the model. If you can keep both training error and generalization error low, then you are good enough. You say, okay, my modeling is good. So by looking at them only, you can looking at them itself, you can tell, right? So there is another issue. Suppose you have two models and you are finding they are comparable models, comparable results, and both training and test, they are comparable. Which one you should choose? Now that is one principle of scientific I should say scientific attitude, or I should say scientific investigation. One principle is that we go for the simpler model, and that's Occam's razor principle. Right? We go for a simpler model, which has better explanation. We try to say that nature, by its law, try to make this kind of processes will always favor the simpler explanation or simpler process. Right? So this is a kind of philosophy. It's a philosophical argument. You could have chosen any one of them, but usually you go for simpler explanations. So there are triple trade-off, as I mentioned, that complexity of the hypothesis, the representation, then the amount of training data, and the generalization error on new examples. So these three are very related. So if you keep complexity low, the training error may be high, you need to increase complexity. If the training error is low, if the generalization error is high, then you need to decrease complexity. Again, depending upon your also training data. So because if you don't have sufficient training data, that may not be good enough to match that complexity. So if you have simpler model, you can work with less data. If you have complex model, higher dependency models, you have higher variables, etc., high number of dependency parameters are there, more number of parameters are there. So you require more data points. So that is also another issue. So the amount of training data is also there. So I talked about this model selections, as you see, number of parameters, for example, degree of a polynomial for regression. So we divide them. Now this is a concept. We divide this input into 3 sets, like training, validation, and test set. And so you see that actually when you develop the model, we train the we use the training set for developing the model and test on validation set and iterate it, so that both validation error, training error is small. Once it is done, then the performance is tested on test data set. So that is the test. So that is the way we go for this, and sometimes we use cross validation. And there are other way of comparing model. There are information theoretic way. So since we are also almost we have just come to the end of the class, let me summarize. This is the end of this topic. Just quickly summarizing the thing. So as you see, concept learning, we have considered the problem as a search in the hypothesis space, and we have seen there is certain kind of ordering in the hypothesis space, general to specific ordering, which gives a version space, concept of version space, and there are algorithms to derive that version space in an efficient way. We discussed about that, and there are inductive bias should be there in the formation of hypothesis. We discussed about that. We understand that what is meant by this inductive bias theoretically, that to make it equivalent to a deductive system. The concept learning algorithms, what we discussed, we consider training data set is error-free, but in general, you will have noisy data. So you should allow form hypothesis with low training error, and we'll discuss in the next topic in decision trees. So supervised learning of a model like classifications, regression. Let us not. So we have discussed about these concepts: model capacity and complexity. We have discussed this dimension, and that is the definition. Number of leveled samples, generalization error. These are the things you should consider. 3 types of errors also, like test error, training error, validation error, test error, and choose a model by keeping training and validation errors low, and perform compute generalization error or check the generalization error by which is indicated by the test error. So with this, let me complete today's class. Let me end this class, and this topic is also over for today. So I will first take your attendance, and then I will take some questions from you. Okay, so if do you have any questions? I think there is no question. So anyway, tomorrow then we will start. Tomorrow in the morning. Yeah, is there any question?
Yes, sir. My question is not regarding the lecture. It was fine. Like I understood things.
Yeah.
But it was regarding the weekly report.
Yeah.
Okay, so in the weekly reports, like we have submitted 2 reports till now.
Yeah, they are evaluating. What is your question? Yeah, you have submitted.
My question is like, can there be a session with the TAs or something, like they can tell us like what they expect and like how we should improve?
It's all right. So I will ask Joystree to set a meeting with you. Okay, and those who are interested, they can join that meeting. We cannot do it in the class hour. Okay.
No. I totally understand.
Yeah.
Not in the class.
In fact,
like maybe after 5.
Yeah. So they have also discussed, and they can share with you their views. Okay. I will talk to them.
Okay. Thank you, sir. That would.
Okay. Then bye. See you tomorrow morning.